Welcome viewers to the sixth lecture of the online course on non-traditional abrasive machining practices, and today we are going to continue with the discussions on ultrasonic machining, and we will take up horn design today. As we have discussed previously, the horn happens to be the connecting element between the transducer and the tool, and the main function of the horn is to amplify the amplitude of vibration. First of all, it forms a physical connection between the transducer and the tool. Secondly, it provides this amplification of amplitude, because at the transducer itself we cannot get the full amplitude, because if we try to do that, we will be unnecessarily putting the transducer material to a lot of stress and fatigue, and it might fail. So instead of doing that, we get a small amount of amplitude at the transducer and we amplify it with the help of this mechanical device called this horn, and we get higher amplitude, our desired amplitude level, at the tool end of the horn. So we have drawn a free body of the horn. First of all, a schematic, within that a free body of an infinitesimal horn element. What do we have here? First of all, the horn is extending horizontally, but generally it is placed in a vertical position, and on the left side we have the transducer end. So this is the place where it is fixed with the transducer at this section, okay, at this end, and thereafter it is shown to decay. The cross section reduces continuously, so that after that it comes to a particular section shown here. We have shown diameters, but the horn does not necessarily have a circular cross section. It might have something different as well. So what do we have here? Here we have taken a cross section, and two cross sections in fact. At here we have put x equal to 0 plane, and from there this is at a distance of x, okay, a variable value, and this particular element that we have shown here, it's having a thickness of dx, okay. So this infinitesimally thin specimen, okay, this particular small body that we have drawn, it is undergoing a displacement given by u at this particular section, and it's undergoing a displacement given by this particular expression at a section shifted by dx value from this particular section. Why this change in displacement? This is because displacement itself might be having a gradient, okay, it might be having a change with x, and this particular derivative of displacement with respect to x, it is multiplied by dx, this infinitesimally small distance, and therefore we get the actual value of displacement at this particular section with respect to u at this section. You might ask me, what is this derivative du by dx, del u by del x? I will say, I don't know. At this moment I don't know, but we can relate it this way, and we can later find out its relation with the other known components, known parameters. So here this cross sectional area of this particular section we are designating as S, and this cross sectional area which is shifted away from it by dx we are designating as S plus del S del x into dx. So now I think viewers can well understand that our idea is this: we are designating some values here, and when we are shifting by dx along the x axis, we are simply relating this value to the values at the previous section by the derivatives of these variables with respect to x and multiplying it by the infinitesimally thin dimension dx. So, in the same way, if stresses are built up due to vibrations as sigma x, okay, the stress, the normal stress parallel to x axis. So, in the same way, stresses sigma x plus del sigma x del x into dx will be developed at this particular section. So, let us take them one by one. So, we understand that at this moment we are talking about, we are dealing with displacements due to vibration and cross sectional areas and also stresses built up due to this vibrational motion. But first of all comes a question, what in which direction is this vibration taking place? This body is vibrating this way, okay. The horn is vibrating this way. At the node points we have no motion, and at the antinodes we have maximum motion. So, first question, where would we like the antinodes to be? The antinode should be at the connection point between the transducer and the node and the horn, and ideally we would like to have this particular point, okay, the cutting, the position of the cutting section or the cutting tool. This should be an antinode point, so that it will be vibrating with the maximum amplitude. At some point in between, definitely we will have at least one node point which will be not having any particular displacement, and at that point we can hold this horn, because physically we have to hold it at some point. Why is displacement taking place? Because as it is executing this sort of vibration, displacement is definitely going to take place. Why are stresses being built up? Stresses are being built up by virtue of this particular motion, because just like in wave like motion, the motion is being transferred from energies being transmitted from one point to another, and it's building up stresses. So, let's start with, okay, first of all, let's take the question of strain. So, what is strain? Strain will occur if the length of a particular section of this horn changes due to the stresses applied on it within the elastic limit. We are talking of elastic strain at this moment. So, how can we find it out? Suppose you ask me, okay, that's very good, I'm really impressed by this idea. So, tell me, is this particular disc undergoing any strain? This small disc of dx thickness, is it undergoing any strain? In that case, I will say that, okay, I will find out whether it's changing its length, okay, along x axis, and then I will divide it by its original length equal to dx, and that's exactly what we have done here. That means the displacement at this particular section is u, and the displacement at this particular section is u plus del u del x into dx. So, if these values are the same, it's not suffering any displacement, but if these values are different, definitely these sections are traveling different distances, or they are suffering different displacements in the same time, and therefore, it's definitely resulting in a change in this particular thickness. So, what we do is we simply take their difference. So, u plus del u del x into dx is the displacement of this section, okay, while u plus u is the displacement of the previous section. So, we just take their difference in this particular expression and divide it by the original length, and therefore, it comes out to be del u del x, and we say that del u del x must be the strain. And since stress by strain is equal to elastic limit, therefore, we equate this to stress divided by elastic limit. That means, elastic limit can go upstairs and strain can go downstairs. So, that you will have E is equal to sigma x by epsilon, or strain. So, up till this point we are simply resorting to stresses and strains and their relationships, and we are satisfied that strain is equal to del u del x. That is fine, and that is equal to sigma x by E. So, all these things that we have discussed, they are formally defined here. U is equal to displacement at section at x, the element dx length is strained as the displacements of its two faces are not the same, etc., etc., etc. So, let us pass on to the next step. In the next step, we are saying that is there any unbalanced force on this particular element? So, why should unbalanced forces come? Before venturing on that particular debate, let us find out simply it is connected to its neighboring material simply by forces occurring on these faces, and let us compute the forces which are occurring on these faces, take their resultant and find out whether it is 0. If it is 0, then there is no unbalanced force acting on this body, but if there is an unbalanced force, it will definitely cause acceleration. So, first of all, on these sections, what are the forces acting? The normal forces. The normal forces, first of all, one is the stress multiplied by the cross section on this one and stress multiplied by the cross section on that one. That is very good. So, we have on one of the faces sigma x plus del sigma x del x into dx, and the area, corresponding area is also s plus del x del x, okay, del s del x into dx minus, okay, this is the force on one of the sections. This is the force on one of the sections, and the corresponding force on the other section is simply sigma x into s. That means sigma x, the normal stress on that face, multiplied by the cross sectional area s. So, this will give us the unbalanced force. So, this we can just multiply these and get the products. For example, we will have sigma x into s, we will have sigma x into del s del x into dx, then del sigma x del x plus del sigma x del x dx into s, like that. So, let us see how it comes out. A number of terms will cancel out. For example, sigma x into s will cancel out with this sigma x into s, etc. So, that ultimately we will get this particular expression. I think it will be a good idea to just have a quick look at the calculations. If I do it here, sigma x plus del sigma x del x into dx multiplied by s plus del s into del s del x into dx minus sigma x into s, and if we expand it, we will have sigma x into del s del x into dx, okay, plus s into del sigma x del x dx plus, oh my, so there are two different terms. Do we have space for that? Yes. Del x dx del s del x into dx minus sigma x into s. That is good. This one and this one will cancel out. This one is, its fate is sealed because it has two different terms. dx is gone. It will be too small for our consideration. So, we have only two terms surviving, only two terms, and it is shown here. Only these two terms will survive, and therefore, we come to the conclusion that yes, there is an unbalanced force on this on this thin element. So, in this thin element, this unbalanced force will cause acceleration. Now, why would it do that? If it has to obey Newton's laws, it has to do that, and therefore, we use a term acceleration. P is equal to mf, P being the force we have already computed, and mf is mass into acceleration, and therefore, some people use F is equal to ma and some people use P is equal to mf. It means basically the same thing. So, on this side we have an expression of density into volume. Cross sectional area multiplied by the thickness will give us the volume, multiplied by rho gives us the mass. So, this is the mass expression, and this is d2u del 2u del t2. That means the second derivative of displacement, which all of you know is acceleration. So once we have this, you can straight cut see that if this is equal to this term, then dx will first cancel out. Dx will cancel out, and do we have s cancelling out? No. Why? Because s is here, but s is not present here. So s will not cancel out. So it seems that apart from dx, nothing else cancels out. But we are making a substitution, which is sigma x. Sigma x was, it was present here. Del sigma x del x. So and also sigma x is present here. So we were not knowing what to do with them. Okay, but now there's a good chance of getting rid of sigma x by replacing it with E into del u del x. This we have proved just now. Stress by strain, and strain has an expression of del u del x. So this is going to replace, and therefore sigma x, once it's replaced and once dx is cancelled, whole equation, we will have S, meaning the surface, the cross sectional area, E being the elastic limit, multiplied by del 2u del x2. Now where does this come from? This comes from the fact that we are already having del sigma x del x here, not sigma x. So derive this with respect to x once, and you will get what we are having here. So naturally E is a constant, so it comes out unscathed, but del u del x gets derived once, and therefore you have this particular term. So we are satisfied that okay, this has been transferred, it has been represented correctly in the next expression, and we go to the next term. What does the next term have? It has sigma x, and therefore you straight away you can put E here. E is here. Del u del x. Now what do we do with del u del x? We do nothing. We simply bring it here, and after that you have del s del x. That's good. Del s del x is also here. All the terms which were causing us a lot of worries, fortunately they have been transferred unchanged to the next expression. Rho was here, we cannot do anything with rho. S was here, so S has been transferred. So only dx, which has been cancelled from all the expressions, that is gone, and we still have del 2u del t2. Now that's a problem, because you don't have any t containing terms here. So what do we do with this? Because this is going to add to the unknowns, and the variable has crept in. What do we do with this one? So for that we resort to an assumption. We say that the displacement is going to be simple harmonic, and it's going to be addition of these two terms to represent a general simple harmonic motion. Okay, these are displaced, with a phase difference from each other by 90 degrees. So we are saying the displacement is simple harmonic. You might say, why? I will say because it's it's vibrating. All cyclic motions they are ultimately simple harmonic motions, and therefore we represent the displacement by this particular expression, the general expression. That's good, but what comes out of it? What comes out of it is del 2u dt2 del t2 comes out to be minus omega square u. This is a standard derivation in case of simple harmonic motion. Simple harmonic motion states that the acceleration of the body is such that it is always directed towards the mean position. When it comes to the mean position, the acceleration is 0. When it goes to the extreme positions, its velocity is 0, but the acceleration is maximum, and it's equal to this one. Why is the sign negative? Because it's always directed towards the mean position. Okay, so now comes the question: how did we get this? See, if you derive this with respect to t twice, you will find that the same thing will come back and you can replace u in that particular place. Okay. So, I am not deriving this, I am sure you can do it. You can derive it twice and you will find that the same thing is coming back, replace u with that and you will get minus omega square u. Now, how does this omega square come? That is because it is sine omega t, it does not look fully like omega, I am sorry about that, it looks more like w, but it is omega, and therefore, if you derive it, it will become a omega cos omega t minus b omega sin omega t. Next derivation, it will become a omega square sin omega t plus minus a omega square sin omega t minus b omega square cos omega t, and therefore, you have omega square coming out common from them, minus sin coming out common, and what is left is the displacement term, which is this one only. Okay. So, the last t containing term is successfully removed and you will have minus omega square u. So, what does the expression look like? The expression looks like this. That means, on the first term we have del 2u del x2, this was coming from the derivative of sigma x, remember, and then comes the middle term, which was unchanged derivatives that we have had to resort to in order to relate displacement and area to the x direction, that is their gradients with x, with 1 by s, and omega square by c square is coming because we have made a replacement now as the velocity of sound in the medium of the horn being root over E by rho. So, let us have a quick look at the expression before this. E is here, rho is here, so that you will get E by rho here, E by rho here. So, 2 E by rho is here, and therefore, you can also say that I have 1 by E by rho here. Okay. So, having replaced root over E by rho by c, you will find that we will have a c square here. Where does this particular term come from? Remember, we had minus omega square u from assumption of simple harmonic motion. So, it comes from there and we have a c square term coming from this particular substitution. That is good. So far, so good. But what do we do with this? We have x, we have u. So, this is one variable, this is another variable, s is yet another variable. What do we do with this? We make now an assumption. The assumption is this: we say that if the cross section is changing with x, in that case, let us take the case of a horn with an exponentially decaying cross section, exponentially decaying cross sectional area. So, the cross section itself is coming down. I do not know whether it is circular, I do not know whether it is rectangular, but simply I know that the cross section is decaying with x by this expression s is equal to S0 into e to the power minus alpha x. What is alpha? Alpha is the way in which it is decaying. It's a constant value. Okay. So, once we have made this assumption, or once we are considering such a horn, we simply replace the value of s by this expression. So, what do we have? We have 1 by s. So, for that, in the second term, in this place we have replaced s by this expression S0 into e to the power minus alpha x. So, what is S0? S0 is the cross sectional area where it connects up with the transducer. At the transducer end, we are having S0. Sorry. So, when we are deriving del s del x, and as it is having e to the power minus alpha x, e to the power minus alpha x will come once again, and it has appeared here. So, a minus alpha will be coming out due to the derivation, and therefore, we have all the terms unchanged, only s value has been put in, and it's a good thing that this will completely cancel out from the numerator and the denominator, so that we'll have, let's see the final expression after this cancellation. That's it. Del 2u del x2 minus alpha into del u del x plus omega square by c square into u equal to 0. Now, just like it's true for the displacement, it's also true for the velocity. If we derive this whole thing with respect to time, del 2u del x2, u can get derived inside and give us velocity, okay, and therefore we can also have this particular expression valid for our discussion. So, in this case, what do we ultimately have? We have a differential equation in which the velocity, or here the displacement, they are related to the distance along x, and there are a number of other constants appearing, and if we solve it, we will be getting an expression of the displacement along x. What is this displacement for? Due to vibration. So, in this case, there are a number of ways in which this particular differential equation can be solved. One way to solve it, one of the easiest conventional ways, is just take the dependent variable to be equal to e to the power mx, where x is the independent variable and m is a constant. Okay. So, if we do that, let's just go to the previous expression once again. This was the previous expression. In this case, e to the power mx, when derived twice, it will give us m square, and e to the power mx when derived once, it will give us m. So, it should be m square into e to the power mx minus alpha m into e to the power mx plus omega square by c square into e to the power mx equal to 0. That is it. M square into e to the power mx plus alpha minus alpha into m into e to the power mx, because e to the power mx after derivation will give e to the power mx once again multiplied by that constant m into omega square by c square is a constant into e to the power mx equal to 0. Once we have this expression, if we have to solve it, e to the power mx can be cancelled out from the expression if it is not if it is assumed to be non-zero, and after that we have this particular expression m, a quadratic equation in m. If you have this quadratic equation in m, we can simply find out its root as minus b plus minus b square minus 4ac, minus b plus minus root over b square minus 4ac by twice a, and that is what we have done. So, here what we say is that if the roots are real, that means if alpha square is greater or equal to 4 omega square by c square, in that case the roots will be real, and you won't get any wave like motion corresponding to that. Okay, understood? So, what do we do about that? We can add that if, however, 4 omega square by c square is greater than alpha square, then you will have imaginary roots, and once you have imaginary roots, it can exhibit wave like motion. Okay. Now, why is this so? This is because we are having this sort of a solution. In this sort of a solution, if the roots are complex, that means if, as we discussed previously, 4 omega square by c square minus alpha square is greater than 0, in that case we will have a solution of this type, and this one will give rise to sine and cos waves. Okay, sine and cos solutions. Okay, imagine, if you remember, this when expanded will give rise to sine and cos, and therefore what we have is this part comes out to be the real part. So, it is multiplied as a coefficient to the amplitude, and this part gives rise to the wave like motion. So far so good. Now we put a initial condition. Okay. But before that, I think our time today is over. So we will continue this in the next discussion. Okay. Thank you very much.